Thank you for watching our presentation. My name is Hadjer Benkraouda and I'll be talking about SNIFU, Secure Network Interception for Firmware Updates in Legacy PLCs. This work is the result of a collaboration between myself, Asif Jakantakath, Anastasis Kileris, and Mihail Maniatakos. Industrial control systems are used to automate the control of physical processes in industrial environments. They manage a wide range of industries, from nuclear power plants and power grids to railroads and trains. The industrial sector has seen many advancements in the last years. This was to ensure better profits and to be able to preemptively schedule maintenance, also to be able to remotely operate these systems. This increase in connectivity and the move towards commercial off-the-shelf devices has exposed these systems to unprecedented threats. This is evident from the increase of attacks that we have seen in the last decade, the most prominent being Stuxnet that attacked or targeted a nuclear power plant in Iran. More recently, you have seen these attacks move towards targeting field devices, such as PLCs and their firmware. An example of this is Indestroyer, which was an attack on the Ukrainian power grid. Indestroyer used a malicious firmware on serial to Ethernet converters that disabled all the connection and therefore the commands to the remote substations. Additionally, these systems present a unique security challenge due to the wide employment of the devices with long lifespans. This results in a significant number of legacy devices. These devices have limited processing and memory capacity and therefore cannot deploy the security mechanisms that are usually proposed and developed for other systems. In this research, we want to answer the question that concerns the possibility of developing and ensuring the security of firmware update processes for legacy PLCs. And therefore, we propose a security mechanism that is non-intrusive and that can be retrofitted to legacy devices. This will be able to leverage external resources to implement the security mechanisms needed externally. This is a general overview of a typical ICS environment. The blue lines follow the data flow of the firmware image to give a better understanding of the possible threats. First, a legitimate firmware image is safely received at one of the DMZ servers. Next, the firmware image is securely and successfully transmitted to an air-gapped firmware repository where it will be signed and stored. From there, the firmware image can be uploaded to PLC in two different ways. It can either go through the engineering workstation or it can be provided through an external vendor contractor. In each of these cases, the PLC that is targeted will be equipped with a security device. In our threat model, we make some assumptions. First, we assume that a genuine firmware image is received at our firmware repository. This assumption includes attacks that originate on the vendor side, including any tampering that has been done before the image was sent from the vendor. We also assume that the device is safe from physical attacks and we do not secure against them. All attacks beyond these two limitations are covered by our proposed solution. This includes any attacker that can get access to the system remotely or to the plant more accurately. The attacks that originate from both IT and OT networks are also secured through this mechanism. To be able to confirm the authenticity and integrity of a firmware image, our solution has to be able to extract the firmware image during the update process. Since firmware updates are interactive procedures that require intermittent responses from the device that is being updated, our interception mechanism needs to emulate the PLC during the firmware update process. This means that it can correctly respond to the tool with valid responses. To be able to emulate PLC responses, we first have to understand the underlying protocol of the update tool. we were able to reverse engineer the firmware update process by examining three main components. We first analyzed the contents of the descriptor file. This included information such as the product identification number, the firmware binary names, the MAC address of the device. We also captured the activity log and the update progress messages. These helped us infer the chronological steps taking place. The firmware update steps included steps such as validating the connection to the device and validating the CRC of the device or of the firmware image. We next performed packet capture during the update process. We used a USB sniffer with Wireshark. After filtering the packets, we were able to extract communication pairs between the update tool and the PLC and understand their functionality. To have more information about the reverse engineering process and the details, please refer to our paper. At the end of the reverse engineering process, we wanted to validate the correctness of the extracted firmware image. We compared it with the original image obtained from the WAGO PLC. The comparison resulted in significant findings, indicating that the firmware binary was getting modified by the update tool during the update process. This meant that the update tool was not only transferring the data, but also made some changes throughout the update process. This included things such as the time and date of the update, the MAC address, and the serial number of the device being updated. This also meant that using digital signatures alone would be insufficient and would always result in showing that the firmware image was modified, even if these modifications were intended. To secure the firmware update process, we propose SNIFU. This is an overview of all the components of our solution. First, our internal repository signs the firmware image. When in transit, SNIFU extracts the firmware image using the PLC emulator. Since the official firmware tool modifies the firmware update or the firmware image before uploading it to the PLC, we devise a two-stage firmware verification mechanism. In the first stage, SNIFU considers the dynamic bytes as stateful and masks them during both the signing and the verification process. During the second stage, SNIFU extracts these dynamic bytes and feeds them to a trained machine learning model that classifies the bytes as potentially malicious or benign. It is important to secure these bytes because they were not verified in the first phase and can therefore be instrumented to carry out malicious tasks if an attacker uses these locations to inject a payload. On the other hand, if these segments were modified with other data, an attacker will not be able to perform meaningful and structured attacks. Now, if both of these verification phases are passed, SNIFU will allow the firmware update to happen. Otherwise, it would block the firmware update through a timeout. The firmware repository, which is an air-gapped PC, signs the vendor-supplied images. The stateful bytes from the firmware image are masked before being passed into the signing algorithm. A SHA-256 hash of the stateless bytes is produced, and then a private key is used to encrypt the hash, which then produces an RSA signature. This signature is then appended to the end of the firmware file. Using the information we extracted from the reverse engineering steps, we develop a WAGO 750-881 emulator that is able to send and receive both device level and firmware loader commands. These interactions with the update tool are what allow the emulator to receive the firmware image that is used or that is going to be used in the two-step verification that we proposed. In the first step of verification, we look at the static bytes of the firmware image. SNIFU receives a signed firmware image from the update tool. The digital signature attached to the firmware during the signing process is extracted and decrypted using a pre-shared public key by SNIFU. The tool also uses the knowledge from the reverse engineering step to extract the firmware payload. Now the stateless payload is hashed using SHA-256 again, and then passed to the verification routine. During this step, the decrypted signature and the newly calculated hash are compared. If they match, then the firmware image has not been manipulated. In the second stage of verification, we assess the dynamic bytes. Here, our main concern is executable payloads, and therefore we ensure that these dynamic bytes cannot form a sequence of executable instructions. To this end, we build a machine learning model that can classify a disassembled binary segment into either a code sequence or a data sequence. Our training dataset was formed from disassembled binaries. For this, we chose an SVM model because they perform well with short text. More specifically, WAGO PLC binaries were first disassembled, then pre-processed by removing operands and appending instruction mnemonics. They were then labeled into either code or data and used to train an SVM model. After training, our model had the recall accuracy of 100%. This meant that the classifier was able to identify all code sections accurately. When SNIFU extracts the dynamic bytes, it first disassembles and pre-processes this sequence in the same way that we saw previously, and then feeds it to the machine learning model, which classifies them into either code or data. If the dynamic sequence is classified as code, this means that it is potentially malicious. On the other hand, if the sequence is classified as data, this means that it is benign. Please refer to our paper for more details about the data sets, the pre-processing steps, and the tools used during these sections. We carried out a case study on the WAGO 75881 PLC, where we examined and were able to reverse engineer 2 versions of the update tool. We also worked with 2 versions of the firmware. In our experimental setup, the update tool, more specifically WAGO FBC update, it was installed on a standard Windows 7 PC. This computer was connected to the bump in the wire device, SNIFU in our case, using a WAGO service cable via a level shifter. The WAGO PLC was also connected to the device with another WAGO service cable. SNIFU runs on a Raspberry Pi and was developed using Python. This means that it is able to be executed on cross-platform systems. Now we come to testing our framework. Here, we signed both versions of the firmware that we were working with using generated keys, and then we ran several tests. In the first set of tests, our main aim was to ensure that SNIFU did not interfere with normal updates, and we performed firmware updates and or firmware upgrades and firmware downgrades, and we also kept the same version with no modification in any of these tests. As you can see from the table, in all of these 3 tests, in the upgrade and the downgrade, and in the case where we kept the firmware image as is, with no modification to the firmware image, the update process was successful. And SNIFU did not interfere with the process. In the next set of experiments, we also worked with signed firmware versions, but in this case, we made modifications to the stateful bytes and to the stateless bytes independently. And we recorded that SNIFU was able to detect these modifications and in turn block the updates in both cases. Lastly, we also ran a test to show that SNIFU also blocks unsigned firmware images, even if no modifications were made. This ensures that the firmware image originated from our firmware repository. We also examined the time that it takes for SNIFU to carry out an update. The results show that the overall time required to perform the update task with SNIFU in place doubles compared to the normal update. This includes the additional overhead to execute the verification routine and update tool startup. It also includes the time required to perform the actual update on the PLC. It is important to note that the two-step verification process takes around 31 seconds only on the device. This is an insignificant overhead since firmware updates do not happen very frequently. It is also important to note that SNIFU is able to perform the verification while the PLC is working without disrupting the functionality of the PLC. Only when the firmware image is verified is the PLC engaged and therefore needs to go offline. In conclusion, in this work, we were able to develop a cost-effective, non-intrusive solution to secure firmware updates for legacy PLCs. In our future work, we plan to extend SNIFU to support additional devices. And we also plan to include PLCs for different vendors. Another thing that we want to explore in the future work is the feasibility of fully or partially automating firmware update reverse engineering processes. Thank you for listening to our presentation, and please forward any questions you have to the emails shown on the slides. Please also feel free to contact us through Twitter on the Twitter handles that are shown on the slide. Thank you.